Alrighty. It is a Monday. Welcome on back. Got a couple things today, not too much actually. So hopefully today will be pretty smooth. Looking at our containers, different abstract data types, ways that we can use the standard template library to store data. Right? This is all built-in stuff, and we don't need to reinvent the wheel, which is awesome for. I'm gonna have chat on my other screen here. One of these days I'll remember how to teach, but probably not on the Monday. Right, let's make sure that loads. Okay. Had a couple questions about the project. We talk about some of those as well real quick, if you don't mind, and then we can jump into the new stuff. Maybe we'll do that while Visual Studio loads. So, project 1, working with inheritance and working with pointers was the goal of this one. Right, so we're gonna have this character class with attributes. Someone had asked about this weapon attribute. So there's a class for weapon. So the type should be the class, right, of weapon here, not a string. Some people love strings for everything, which is, you can store a lot of info in a string, but if we have a class for a weapon, right, you should do the type of weapon here for that. Okay, I think that was the biggest question. I know it's a little rambling here. Had some fun putting this one together on Wednesday. But in practice with inheritance, practice with pointers, making sure we get that cool runtime polymorphic behavior, should be okay. I think someone said they turned in a lab here by mistake, but maybe not. Maybe someone actually finished it, but we got a little time on that one. All right, so we start up a new project here for our containers. And we'll add our source file. Okay, so we've done vector, right? When we include vector, everyone's relatively familiar with these ones by now. Had a lot of fun with them. They're great for storing things, right? They're extendable. We can add stuff to the front. We can add stuff to the back. Just keep on pushing back as much as we want. You can do some other cool things with them as well. One of the interesting pieces here is when you want to loop over them. So if I have a vector of, we'll say, string here, and we'll just call this names. And we can add a bunch of names, right? I push, and say I wanted to add some in lowercase. Push back. So I've got a couple lowercase names. If I want to loop through them, we've got a couple options. The most common way that we'd loop through them is by index, right? So for index 0, index is less than my name dot size, index plus plus. Right, that's our common loop. And then we can do something with that at notation. So if we wanted to, we could see out, hey, names dot at the index. Right. This is relatively straightforward. If you don't like typing a lot of things, though, we've got shortcuts. Right? Have you seen the enhanced for loop? We're going to say for string name names, let's see out the name. Right, so this says for every name in the names collection here, I want to do something with name. So each time the loop goes over an item, we're going to call it name inside the loop, and we can do something with it. Now, what you can't do, though, here with this basic loop is I can't really change name. So if I said, hey, name equals, what do we want to do, like test. Let's change the value of name. When we see out the name, it'll be fine, But when I run it again here, we're not going to get any differences. I give this a little run. We can change it. It's temporarily inside the loop here with my variable for name. They look like test and test here. But then when I run it again, they haven't actually changed. Or if we put it in debug mode, we see they're not changing. Because what's happening is we're changing this local variable test, the local variable name, to the value of test. And so we're not changing it directly. Now, if you want to change the things inside of your list, you can, though. The at notation is probably the easiest way to go about that, but we have a shortcut in this enhanced for loop as well. If I loop through and say, hey, I want the reference to name, now I can go through and change some values here. And let's just put this one in debug mode because that's fun too. So if we have the reference to where the string is, and I go change its value, now we can change it. So this is my names list here, my names vector, right? The thing stored at index 0 now is test because I've changed what's stored there by reference. If you give me the reference to your string, I can go change what's stored in memory there, right? Which seems to make sense. If I know what's stored, where you're storing it in memory, I can go do it here. When I just do a regular loop here, I'm not getting the direct string reference here. I'm essentially getting a copy. So if you're getting it by reference, we can go change it, which is fun. So we can change those individual values here. We'll step back to the next name. Okay, so now name is currently Jasmine. We're going to go change name here to test, and it's been updated inside the vector. Okay, so looping by reference is pretty powerful if you want to go change it, and it's slightly less typing than doing the at notation, right? What's nice with the at notation is you get the index if you wanted the index number, right? If you think that number is useful, then great, we've got it. Otherwise, we don't really need it. Okay, so that's a fun little hint. I don't know if you had done this before with the enhanced for loop or not with references. Is this new? Wait, you're doing new stuff? I love doing new stuff with you folks. Like, I don't want to waste your time doing a bunch of review, so the new stuff is exciting for me. Happy to do new things. Okay, so we'll take a look at a couple other types here. So the list type is from our standard template library. And what's cool about list is you can push to the back or push to the front. So if we include list here, we can make a list of something, right? With our vectors, I say names dot, I get a couple things here. Oh, names dot, come on, my scroll. But really, push back is all we get, right? So it adds to the end, which is fine. Right? That's all well and good here. But if we wanted to make a list of, say, integers here for, how about our lotto numbers? Why not? When I take lotto numbers dot, I get two options. I can still push back, but I can also push to the front. Remember, with a list or a vector, the order matters, right? So they're put in the order in which we put them here. But if I want to put something in the front, now it's the first thing rather than adding it to the back here, right? Not the most interesting case for this example here, but if we wanted to ask the user, we could, right? And figure out where we need to put these things maybe. We could add smaller numbers to the front, bigger numbers to the back, or, and I don't know, any sort of option here, but we can push front, let's push a 10 in the front, and then push to the back, how we push a 20, and then we'll push to the front again, how about a 5, and then we'll push to the back, how about a 30, sure. Right, then again, with this collection here, we've got our enhanced for loop is probably the easiest way to loop through it if you want here. But there is no at. Right? I can't say, hey, give me something at a given index here. The idea with these lists here is they are a doubly linked list, which we'll get into later. But what that means is they have a connection to the next item in the list, and the next item in the list, and the next item in the list. The order matters, but we don't have immediate random access to any given index in the list. Hector, my friend, thank you so much for donating to the Student Scholarship Fund over here at the University of Michigan Dearborn College of Engineering and Computer Science. I didn't take a breath first. That was a mistake. I know, like, it seems like doing a little dollar at a time doesn't add up much with as expensive as tuition is, but you know, we're getting there. We're getting there. So, trying to pump up that scholarship fund for sure. So, with a linked list, we don't have immediate access to any given index. So the way that it's stored is different, and we're actually going to get into that. We make our own linked lists in a little bit. Find our schedule here. Where do we do that? Yeah, so we are going to build our own linked list later on. I know it seems a little silly to build our own if there's already one in the library, but the idea behind building your own is so that you understand it better. Right? So there are performance implications. Now that we start talking about these containers and abstract data types and ways of storing data, the performance of these different types matter. Because some of them are faster at some things and some of them are faster at other things, or slower at some things and slower at some things, fast at some things for these different types. So as we start making applications and we start thinking, you know, probably actually want this to run fast, this sort of stuff matters. Right? For all of 150, pretty much, and for the stuff we've done before, we don't really care because they're small. Right? We're not dealing with any large amounts of data, so it doesn't really matter if it takes it 3 times as long because it still happens like that. Right? But as we start scaling and making larger applications and dealing with more data and holding more things in memory, if it takes you 10 operations to do something versus 1 operation, and you have to do that thing 1,000,000 times, one of those is clearly faster. Right? So it'll start to matter. So we want to start looking at some of those performance implications of these different types here. And linked lists are really fast at some things and really slow at other things. So vectors are really fast at getting something out by index. Remember, we've stored an entire chunk of memory, and I can jump to any index in that chunk of memory. Right? That's why we're zero-based again. We start at 0, right? It's that's the start of the vector there, of the array, that dynamic array. We just have a chunk of memory. I can jump anywhere. With a linked list, or this list from the standard template library, you don't have that. Right? These things can be anywhere in memory, and they just know where the next one is. It's like following a chain here. Like, who comes after you? All right, who comes after you? All right, what's next? What's next? So what that means, though, is adding something to the front super fast. Right? So I can just add something to the front. It happens immediately. To try and add something to the front of a vector, I have to shift everything down, and if I've got 100 items in there, I have to shift 100 things to make room at the front to stick a new thing at the beginning. That's pretty slow, right? And the more things you have in there, the slower that gets. So if we're doing a lot of these manipulations, specifically around the front or any given location, the list is going to be a lot faster than the vector, right? Which is fun. And then other cool things we can do with our Lotto numbers is we can get an iterator. Iterator is just a fancy term. It means I can go from one part of the list and hold a reference to it, essentially. So we've got all these different options. You got the front, you got the back. You can remove the back or remove the front with pop front, pop back. You can remove by item or by value, just like you could remove from a vector. No, did we have this one? I don't think we had this one at vector, did we? Was my name stuff? Yeah, we didn't have the remove. Right, that one again doesn't work quite as well. There's ways to remove from vectors. It's a little more complicated, but we want the iterator. And these iterators are crazy, but it's okay. So we're going to take the list iterator type here and say, hey, I want an iterator to go through it. Usually we can just loop. So we'll say, hey, I want for, and then I'm going to start with my iterator being the beginning. Sorry, that's coming out a little small there, isn't it? Zoom this in a little bit. Oop, that might be too much. At the beginning here. So we can start with my iterator. I think iter's probably okay here. An iterator, it's not too much harder to type, but you know, we can. is my lotto numbers from the beginning, and then this needs to be my type here. This is my list of int iterator. So the type specifically is given my list of integers. So the list of whatever type I'm using scoped to the iterator. Some weird notation, but it's not too bad, I promise. So whatever type we're using here, colon iterator. I don't know, iter's bothering me. We'll just call it the iterator. Okay, starts at the beginning. So we can ask the lotto number list, hey, where's the beginning of your list? Well, what we have here is essentially a pointer. This iterator here is really just going to point to where that thing is. And we want to loop as long as my iterator does not equal my lotto numbers.end. Where's the end of the list? Right? Then we can do that silly pointer arithmetic. I can say iterator plus plus. Just keep on adding to the iterator. Right? When we had our dynamic arrays, we could take a pointer and you could say pointer plus plus. And you're like, well, I'm not adding 1 to the pointer. I'm jumping the amount of size that we need to here. Now, this one's not really jumping the amount of size. It's actually going to the next pointer, which is kind of fun. So then we can see out my iterator and then line. Oh, but we can't just see out an iterator, right? We need to dereference the thing we're pointing at, because it's essentially a pointer. Right? Iterators are essentially pointers. I can't spell. I'm happy to put more comments in for you folks. I apologize. I've got the bad habit of just never commenting things, so please just shout at me. Happy to throw these in if that's useful. Because sometimes you don't remember the things I say when you're just looking at the code, and that's perfectly valid. So just holler at me, and I will try and put them in. You just got to remind me sometimes. All right, and we get 5, 10, 20, 30, which I think is correct, right? Because we pushed to the front a 10, pushed to the back a 20. We added a 5 to the front, so we have 5, 10, 20, and we added a 30 to the back. So 5, 10, 20, 30. Right? Because we added them in that particular order, because that was fun like that, I guess. Right? So the order still matters. We still have an order, but now it's a little more flexible. Right? And the other cool thing we can do with our iterators is I can start adding things at any given position. I can insert into my list if I have an iterator, and it will put it before that iterator. So it'll become essentially that new position here. And you can also erase something at a given position, or erase a range from here's this iterator to this iterator. You can take it out of the list. So if we wanted to ask the user for a number here, let's ask them for a number. Let's see if we can do this here. So we'll see out, enter a number, add to the lotto ticket. And we'll get an int for a number to add, and we can see in my number to add. Right? Now I want to start iterating. So I don't necessarily want this for loop here, though. I just want to do something. So we're going to start with the beginning here. And then I want to see, hey, if my number to add is less than whatever the iterator points to, I want to go add to it. Right? So then we can take my lotto numbers and I want to insert at the iterator position the number to add. So it will go put it in beforehand. That's only going to do it one time, though, right? It's kind of a bummer. We probably want to do this, right, until we've got to the end. So maybe we'll say while my iterator does not equal my lotto numbers.end. We'll loop this here. If it's less than, we'll insert it, and then maybe we just break the loop. Is that it's a little? I don't usually like breaks, but I think this is probably solid here. Right? Once we've added it, stop the loop. Right? If you don't like breaks, we could also add a Boolean flag or some other options. This is probably okay. Now, if we haven't ended though, if we didn't break, right? What if we gave it the largest number? Is this going to add the largest number? Right, if I tried to add a 40, am I ever going to be less than the dereferenced thing I'm pointing at? No. So it's not really going to do what we expect here at this point. It's not great. So maybe we do need, instead of the break here, we need to say, you know, if we've added it yet or not. Maybe we can have a little Boolean flag. We can have a bool. I don't know what we want to call it. Have added number. That's a little ugly, but that's probably okay. Or maybe we want to set it to true because that might be easier. So need to add number, and we'll set that one to true. And then maybe we can loop while both of these. While we're not at the end, right? And we need to add the number. So then instead of breaking here, we can just say need to add the number is false. Add number is false. That should stop the loop, right? Or if we get to the end, this is false and the loop stops, right? And then once the loop is done, we can check, hey, if need to add the number, then we should add it in at the end. Well, to add at the end, we have the iterator. We know it's pointed at the end value. When we use this insert command, it inserts before the thing we're pointed at. So inserting before the end should put it at the end, right? Or we could just push back, right? Either way is okay. Push back, maybe that's easier, or maybe we can keep our iterator. Pushback's probably easier, right? A lot of numbers push back. The number to add. We can go and add it, right? And then when we're done, let's go through and loop all these. So let's just print them all out. Numbers. Oh, is it not? Oh, lotto numbers. We'll go ahead and print the lotto ticket. See if we actually added it here. Right, so this idea that we can use this iterator, it's essentially just pointing where are we in the list, where are we in the list, where are we in the list, where are we in the list here, and I can insert in any location we want. So what number should we add to our list, to our lotto ticket? What's a lucky number? That's also a joke because they're random. One number is not luckier than another. Go ask your statistics prof. That's a way to get them really upset at you. Ask them what numbers are lucky. Guarantee they'll get upset with you. Well, maybe not upset with you, but you'll probably get a lecture. Seven? All right, I like 7. 7's a good number. Uh-oh. Looks like we're infinitely looping. Well, let's go see if we can't pause this sucker. Pause. Look at that. Hey, we're in the while loop still. Who knew? If we never change our iterator, we're always stuck at the beginning, right? We started at the beginning. We never changed it here. So we should probably take our iterator ++. That'll probably stop the infinite loop. What do you think? That was totally on purpose, just to illustrate that. The debugger here is fantastic, by the way. If you didn't know you could pause it, that's super cool. You just pause. 7, there we go. And now we get 5, 7, 10, 20, 30. Looks like it put it in the right spot. We've accomplished our goal. Okay. Now, adding something super fast once you know what position you need to add to. If I have 1,000 numbers in my list, though, and I need to check, say, the first 900 of them to find where the right position is, that's going to be a little slow, right? But once I have that iterator at position 900, whatever, I can add immediately. We'll call that constant time. There's some other fun numbers we'll look at, and you'll have all sorts of fun in algorithms analysis talking about these numbers here. But constant is really fast. It's essentially as fast as it gets. It means no matter how many items I have in my collection, it's still the same number of operations to do it. It might be 5 operations, it might be 15 operations, it might be 1 operation. It's just constant. Right? It has no relation to the size of the collection. That's why it's constant. Constant speed things are nice. Getting to that location, though, is slow, right? That's going to be determined by the number of items I have. If we wanted to make this list a sorted list and add in 1,000 items, on average, you'll probably pick something in the middle, right? If we average this out. Sometimes you'll be at the very front. We'll have to just check one number. Sometimes you'll be at the very end. We'll have to check all the numbers. Sometimes you'll be in the so on average, you'll be in the middle, right? So half of n, like if we have n items in our collection, half of n is still related to n. So the bigger n is, the more n I have, the more items in my collection I have, the slower this thing will be, despite it being half as many n, right? So that's a linear relationship with n. Right? The more items I have in my collection, the longer the sucker takes to try and find that position. That was a line, by the way. I'm drawing a straight line in the air on my imaginary graph. Just there's a graph back here, right? Could write it in chalk. Actually use the chalk. I think there's a whole box of chalk here. I didn't know they still used chalkboards. I thought everything was whiteboards by now. Apparently that's a whole debate, and they had an issue that some rooms had whiteboards and some rooms had chalkboards, and some people really wanted one or the other rooms. I don't know why. I'm so glad I can do stuff on the computer because you can't read my handwriting anyway. That'd be real bad if I was trying to write code up on the. Why would you put code on a whiteboard? I don't. That confuses me too. So that's okay. Did anyone ever do that? I guess in the lab sometimes I'll like scribble notes on the whiteboard, but not like here's a program. I don't know. I'm confused by a lot of things. So, all right. So this insert operation, insert is really fast, constant, right? Getting there, the location to insert, not so fast. That is what, average of n, half of n, whatever happens to be, right? Half of n items, sure. For our lotto numbers, where you have 5 numbers in a ticket, we don't really care. Not going to be too slow because there's only 5 things, right? If you're playing some nonsense lottery games that have like 39 numbers, then it's going to take a little longer here, right? Not too big of a deal. But the speed does matter eventually. All right, so and then you can erase items, which is awesome. You can loop through, and you can loop through by reference again as well, if you want out of a list, if you want to modify items, which is fun. Yeah, cool. Yeah, removing stuff and removing items as you pop through is a little funky here, but you can. Right? Generally, modifying a list as you're looping through it will do weird things, right? Okay, that was the list. So lists are cool. We'll look more at them later. Again, we'll build our own linked list. Pair, yeah, is that a question?
So we still can get
at a given index. So we could on our own by iterating through it, but it doesn't give you a method like at. So we could make our own essentially to go count there, but it's not there because it's going to be slow, right? It sort of tries to hide that method at. We could count and get there, but it's going to be slow. So you'd have to iterate yourself essentially to find it. Yep. Yeah, so there's no direct index-based notation here with our lists. Pairs are fun. We're not going to do a whole lot with pairs, but they give you 2 items, a first item and a second item, which is fun. And then you get a first and a second, right, in the pair. Something first, something second. This is in the utility library here. You can get a pair, and you tell it what types of the first item, what type is the second item. And then you can access them, you can modify them, you can change them, you can pass around a pair, which is kind of fun. So depending on what you're doing, if you just want to return 2 values from a function, you could have someone pass you something by reference. You could set the value of the thing by reference, or you could just return a pair here. Like, hey, I'm going to return two things. Here's a pair of things. Here's your first, here's your second. We've got options. This one's kind of fun. And then behind the scenes, pairs are used internally. This map thing we're going to look at next uses pairs. Here's the first and here's the second. Maps are much more interesting than pairs. So maps are widely used in the industry because what it lets you do is do this thing that's a key and a value. So usually we say, hey, there's a type of key and a type of value. So I'm going to say I have a collection of keys, and this is a set of keys, if you like set notation, right, where you don't have duplicates. Yeah.
Oh, isn't it like dictionary?
Yes. Yeah. Python dictionary is a map. Yeah, Python's much nicer, but that's okay. We're learning C++. Yeah. So you get specifically a set of keys, a unique collection of keys. So you can't have duplicate keys here, and then associated values with those keys. So we can go through and set up a relationship between those pairs. Right? Each key and value is a pair here. There's a unique key and an associated value. That makes up the pair here. And we'll have that collection. The function uses mplace. I don't like this one, but it's mplace. Sure. What's fun is if the key doesn't exist, it adds it. If it does exist, though, you're out of luck. It didn't change anything here. So let's include map here. Include map. And then some handy things for map, right? If we want to relate some piece of data with some key, we can do that. Now, classes are pretty good at this sort of thing too, where we can bundle them all together, but this is pretty quick. Like, hey, I've got one thing to relate to one other thing. Maybe you don't want to write a whole class for this, and that's okay. That could be all right. So we'll say here, I want a map of type string, and how about double? We'll call this grades. So I can take grades and I can mplace. Well, what's the key value here? So let's give Jeb a grade for my class here, and let's say he's got we'll say how about a 92.2, right? We use the double. Might as well have some decimal places here. So we can go and add something to this collection here. This needs to be a unique key or it doesn't work. Right? If it already exists, you don't get an update. So this is add only. Add new key or it gets ignored, which is okay. All right, and then we can mplace underscore, we'll add journey, say maybe she's doing better here, and then we'll add place. Add Genevieve, and say maybe she's got a 75.9, and place, and we'll add Jubilee. Maybe she's doing like an 83.9, sure. We'll just add a couple of keys here, right? So we get unique keys and their associated values. So we can have some collection with a relationship between the two. So strings are fine, numeric values are fine, right? Anything that you want as a unique key is okay. Whatever you want to use for storing this data, totally up to you. And then what's the value that's associated here? Okay, so we can add a bunch here, and then to get the values back out, use the at notation, which is crazy here, but that's okay. So use the at notation. Where's my little chart? I want my chart. Here we go. So at will return the value associated with that key and even let you change it here. So if you want to change someone's grade, you say, hey, give me my map at and assign it a value. So at is for getting the associated value or setting the associated value. So if I wanted to see out grade for Jeb is going to be my grades dot at Jeb. And because these are unique keys, and remember C++ is case sensitive, capital J Jeb, different than lowercase j Jeb, right? Case does matter here. So at gives access for getting and setting. Right, so if I want to change Jeb's grade, we can just go change it. Let's give him 100 here, and then we'll see if we changed it, right? So give us the, we just run just this one here, maybe? There's my way to just run this. Run to, I don't think that's the option I want. Nope, that wasn't the option. That's okay. I'll just run the whole thing and give it a number. Right, so the grade for Jeb changes. Right, the at notation lets you change. It seems really weird, but that's the same way it worked with arrays or with vectors, right? You change with that, so hopefully that's familiar. If you want to see if you have a key, you can use count, which if it exists, it's in there once because it's a unique set. You're not going to have more than one. Or if it doesn't exist, you're going to get 0. It's not in there at all. You can erase a key, or you can clear your entire map if you want to just get rid of everything here. So this will add new ones. So you could say, hey, if this key doesn't exist, let's go add it, right, with in place. If the count is 0, in place. Otherwise, if the key does exist, use at. So we have to do a little bit of checking here. Did we do random numbers yet? You done random numbers in C++? Haven't? Okay. Number generator. Just the rand function, right? Is that rand and srand? Geeks for geeks. Here we go. This has got to be good. Wow, thanks. Need any of that. Just rand is going to give me too large of a number, right? So I want to do something else. And if you seed it to your time, right? Sounds familiar for some people? Okay, cool. So random numbers are fun. Right? If we wanted to go and say, I like dice. Dice are fun. And there's a lot of like math behind dice because, you know, generally you get a pretty good distribution when you roll a die. But if we wanted to illustrate to someone the sum that you would likely get if you roll 2 6-sided dice, right? If we're playing Monopoly, right, and wanted to go around the board, we roll 2 6-sided dice, right? The most common roll you're going to get is a 7, right? Because you roll 2 dice, add them together, because there's the most ways of getting 7. Right? You can get 1 and 6, you can get 2 and 5, you can get 3 and 4, you can get 4 and 3, 5 and 2, 6 and 1. So there's 6 different ways to get 7 out of rolling 2 dice, and you know there's 36 different possibilities when you roll 2 6-sided dice. So 1 out of 6 rolls with 2 6-sided dice will give you a 7. Right? 1 out of 36 rolls will get you a 2, and 1 out of 36 rolls will get you a 12. Right? This is just looking at that probability. You get a nice little probability curve. You guys all look bored already. I'm sorry. Started talking numbers. But if we wanted to, say, go and chart this ourselves for fun, we could do that. Right? We could say, hey, let's go and see how often we get these numbers here and build our own little distribution, which is kind of fun. So if we wanted to make a map of integer for the sum and integer for the count of times that sum was rolled, we could do that here. This is our sum count, right? And then I could say, hey, let's go for int sum is 2, sum is less than or equal to 12, or just less than 13, whatever you want to type here, sum plus plus. We can take our sum count and we can emplace by sum and 0. Like we're going to say, okay, let's go add a placeholder here for all the possible sums, 2 through 12. So 2 has been rolled 0 times, 3 has been rolled 0 times, 4 has been rolled 0 times, 5 has been rolled 0 times. You don't want me to keep talking, right? So we add a bunch of zeros. Now we want to go and generate some random numbers here. So let's do this seed here. And then we'll generate some random numbers. Now, to get random numbers, we should modulus that random, because we know it's going to be some large number here. So if we take the mod, so if we want numbers 1 through 6, right? So int, how about say for int roll is 0, roll is less than, should we do 36 rolls? Right, and see how many we get. Roll plus plus. Let's take an int for first die is random number modulus 6 should give me 0, 1, 2, 3, 4, or 5. Yep, plus 1, perfect. And then an int second die is a random value mod 6 plus 1. That's die 2, right? The sum then should be those together. First die plus second die. Okay. Then I know I'm going to have a value at sum count already because I've added 2 through 12. So I don't need to place anything. What I want to do is add to it. So I'm going to take my sum count at the sum, right? Give me the value associated with the key of sum, right? So I'm going to have keys 2 through 12. Those are my keys here. Let's take the value there and add to it. Add 1, just plus it, right? And then when we're done, we can print out our results, right? So we'll say, okay, now for int sum is 2, again, sum is less than or equal to 12, sum plus plus, see out. Do we just want the counts, or we want, how about the sum, and then maybe a colon, and then the sum dot, sum count at the sum, get the value associated with that sum. So here's the sum, like 2 or 3 or 4, and then give me the value associated with that, which is how many times it was rolled, right? If it's exactly perfect, we'll get 1, and then 2, and then I forget how the numbers all land, up to 6 for the 7s, and then going lower again here, which is a nice little distribution. But it shouldn't be exactly perfect, right? Because it should be random. But the more we do, the closer we'll get to a perfect distribution, right? The more we try it. But we're just doing 36 times. Let's see what we get here. Right, so we saw, we got no 2s. We had 3 3s, 7 4s, 1 5, 4 6s, 4 7s, 7 8s, 4 9s, 2 10s, 3 11s, and 1 12. Okay, it's random, or random-ish, right? So not a perfect distribution. We only did 36 times. So should we crank that up some more? Let's have a let's even ask the user here. So let's see out how many rolls should we do? An end line, and we can have an int for roll count, and we can see in the roll count, and then we should do this less than roll count number of times. So then we're outputting here, we should give them a percentage then, right? Because if I just have numbers, it might be a little harder to compare. So we could take that divided by the roll count, right? We'll see how many times it was divided by the total number of rolls. We should get some sort of numerical distribution. What is 1 divided by 36? Right, 1 divided by 36. So 2.7% of the time, right? We'd expect to get that. We could do some pretty number formatting and stuff too, but I'm not too concerned. We could get to that later. All right, add a number. All right, how many rolls should we try? Probably more than 36, right? See if we get a better distribution. Usually like 360. Sure, okay. Oh, we did integer division. You guys have to yell at me when I do stupid things. For real, it's okay. Just yell at me. Just make me stop. Okay. All right. Sure. So if that one's a double, will that divide better for us now? We should get a double result, right? Not an int divided by an int. Okay. All right. And let's add 360. Okay. Cool. So these percentages are looking a little better here. If we multiply them by 100, it might be prettier, right? Because then we can read percentages. I don't know about you, but I'm dumb at math sometimes. And okay, 18%, I get it, but it takes me a minute to look at it. Let's multiply it by 100 times 100, and then we'll even stick in there a percent sign because we're going to make it pretty, right? All right, 10 and add 360 rolls. Look at that. Now we get pretty percentages. So around 2% or so. Nice. That's more than 6. 1 out of 6, right? 1 out of 6 would be a little bit less. yeah, so it's more common in our chance here. We got a lot of 8s, more 8s than 6s. Yeah, that's okay. But this is sort of how the distribution falls, what you might expect. If you guys play the game Settlers of Catan, anyone played Catan with the hexagon tiles? You build a little map. So one of the things with Catan is you roll the 2 dice to see what resource is being produced, and all of the number values here 2, 3, 4, 5, 6. There's no 7. Well, 7 means special things, right? So you move the robber at 7, right? But then on through, they will give you a number of dots to show you how likely it is that number will be rolled. So 6 and 8 have the most dots, right? 2 and 12 have the least amount of dots. So it's a quick little visual representation for someone to like, how likely is it that this number will be rolled, right? And actually, I think the dots are the number of even times that it will roll. No, because they don't have 6 dots. I don't remember, but they have dots, right, to show. And this is kind of nice to use a map here. We could have done this without a map, right? We could have just had a vector and used the index to represent this sort of thing. Totally could have done that. I didn't need the map notation for it, but it makes it a little nicer for us, right? Because I have the key and the associated value, right? Key and its associated value. That's the idea with the map. Now, it was pretty easy for us because we preloaded all the keys. We didn't have to check to see if they existed or not here. Right? We could have checked to see, hey, if that key exists, then just add one, otherwise emplace it. Right? You got lots of options. So maps are really fun. You can do a lot of cool things with maps. Get keys and values out. This square brace operator works for adding values, which is actually pretty handy, but you'll get defaults, which you got to be a little careful of sometimes here. So like if you try and get something out and it doesn't exist, it goes and adds it. So you have to check to see if the value exists first. With the at notation, it will just raise an exception here, an out of range exception, if that key doesn't exist. So just like with vectors, using at is safer to get an index because it'll crash if you give it a bad one. At is safer than using that square brace notation because you probably don't want the default. You probably don't want it to go and add a new key when you just wanted to get the value associated with it. So at is generally safer, but you will see people using square brace operators. It's pretty handy for that as well. Okay. Insert. We don't generally use it just because in place it's easier. Right? That's all. All right. Awesome. A set. Unique values. Right? We talked about a map having a set of keys, just a bunch of unique values for a given type here. So it can make sure that we can go and manage those unique values. Right? And it can tell us if it contains the value or not. So sets are fun if you want to do those, right? If you want to have that list of unique values, you can have the set. You can insert, you can erase, you can count, you can 0 or 1 here. You can get the size out. Tell me how many items are in it, which is nice. Do we do that with our map? I don't think we do that with the map. So if the key exists, where's our functions here? Right? There wasn't really a loop, right, for our map. Right? There's no like index notation. There's no first really with a map. One of the things when you talk about maps is there is no guaranteed order. So just because we've added something doesn't mean we can get it back out in the same order, but usually we're doing things by key anyway. C++ map keys. Wow, that was fun. This one any good? So you can iterate over your map, right, using the iterator if you want. What you get when you iterate, right, is you get the first and second values. You get the key and the associated value. So like pairs had first and second. A map is just a collection of pairs where the first value in the pair is a unique collection, right? A set of those keys. So sort of kind of combining some of that notation, right? Do you want to see? Should we do that just for fun here too? So we have it in our code. Sure, we can do that. So we want a map of int and int, iterator is my sum count beginning. Whew, man, while the iterator is not equal my sum count end, iterator plus plus, cout. So we want the key and the value, yeah? Auto's really handy. I should use that more often. I kind of like showing it here just so you see it once, but yeah, auto's super handy. We should probably use that more often. We being me. I don't know why I think I'm royal. Maybe I'm next in line for the British throne, but is it weird they still have a monarchy? Like, that's still a thing in this 2022? Like, we care who was born to who, and there's like hereditary line for who's king.
What power do they use?
Ceremonial power. Yeah, I don't get it. But that's okay. Sometimes traditions are fun, and that's a perfectly valid reason to have a tradition, just because it's entertaining, right? Like that's perfectly fine. You guys should enjoy things in your life. Please do. Like if you're not enjoying something, you're doing it wrong here. And I get school's hard and stressful, and like if you fail, bad things happen and that sort of thing, and like that adds a bunch of stress. But you want to have something that's fun in your life for sure. So yeah. Anyway, so we got to find the first thing. So we want the key. So that'll be my iterator first, and then the value, colon value, dash value, sure. The iterator second. Right, we're not dereferencing this directly, right? Because I want to get the first thing and I want to get the second thing out here. So you can kind of see, it's even showing me that this is a pair. I don't know if you can see that real small IntelliSense saying, hey, that first is a pair of int, the first value stored in that pair. Like as we're iterating through, we're getting a pointer to the pair, essentially, and an end line. Oh, not two of those. Okay, so you should be able to loop through that way and get key and values back out as well. Excuse me. 10, 360 again. Right, here's the keys, here's the values. Now, we happen to get them out in the order we put them in. So that's not going to be guaranteed. Behind the scenes, eventually when you start adding enough keys, it'll have to shuffle things around. You can learn all about that in the algorithms class, that other sort of stuff. But you're not guaranteed to get them out in the same order you put them in. So just keep that in your back pocket. So, all right, so we can get them out with the same sort of iterator here as well, which is cool. Okay. All right, so that was our maps. Sets are fun, just a unique collection of values here. Sets are fine. I don't think you need to do too much with them. Insert, erase, count, size. Those are good. A queue. Now, queue is a funny word because it has 4 silent letters. Right? No? Okay. Nothing? I'm trying here. I'm trying. The queue. It's only the queue, right? Everything else is silent. Technically, they're not silent. They're just waiting their turn. Oh, there we go. There we go. There was a groan. That was a terrible joke. I mean, it's true, right? So an ordered collection here that inserts at the end or the tail and retrieved from the head or the front. Yeah, first in, first out, your classic grocery store line, or if you're British, a queue. They call them queues instead of lines, and we call them lines because language is hard. Like American English is definitely diverged from British English. So I don't know. I had as a kid, my mother had a business trip out to England for something. I forget what it was, and she brought back a book, and she's like, "Oh, hey, I heard this book was really popular," and it was Harry Potter and the Philosopher's Stone, is the British version of the book. And for Christmas, he got a jumper and all sorts of British words, which was fun to read as a kid. I didn't recognize half the terms for some of these whatever they called them, but I had the British copy, not the American copy, which was fun. I think it's at my mother's house still. I don't think I took it with me. But anyway, a queue, right? They had queues for things instead of lines for things. That's where that story came from. So you can push things to the end of the queue. You can look at the front of the queue, or you can pop it off the front of the queue. And we're going to build our own queues as well, because it's lots of fun. And again, looking at performance, some of these things. So all of these operations are really fast, which is fantastic. The queue doesn't let you get things out of other locations, right? You can only grab the thing in front, which is generally pretty good. So no one can skip the line, right? You always get put at the back of the line. You always get taken off the front of the line. Life is good. People like lines. They're generally fair for that sort of thing. Although now there is no like fast lane or like, hey, I only have 15 items or less. I want to go to the short line here at the grocery store. This doesn't support that. Right? We don't have that sort of operation, but that's okay. So we can push, we can pop, and we can look at the front with our queue. Doesn't seem like it'd be all that interesting, but if this sort of model fits what we're doing in our code, it keeps us from doing bad stuff. Or if we're going to give this to someone else and say, hey, here's a bunch of data that my program has, I'll give you a queue of that data. They can only interact with it in that manner, which might be appropriate. So some sort of like messaging systems. If we're getting messages from something somewhere, right, we're going to add them to our queue. They need to be processed by someone else. Our job is just to collect the data. If they want to go and look at the data, they've got to process it off the queue, because here's the first thing, here's the next thing, here's the next thing, here's the next thing, right? Look at these alerts in order, or some sort of stuff like that, right? If we expose just a queue, then they have to work it in order. And if they ignore things, that's up to them, right? So it sort of fits this idea that we are going to design our program to maintain its integrity. And we're going to give you access, right? That the public API or that abstraction you're going to work with is, hey, this is what you get. You get to work with it. So it's not the most common use case for needing a queue, but sometimes our data naturally fits in this queue model. We can say, okay, here's a queue, you go work it. You go do what you want here. And queues are pretty fun for that. The deck, don't know how this is pronounced deck. I guess the UE is silent, right? And a Q without a U actually sounds like a K, because English. Really, I don't actually know. I'm not sure. But this is deck. Sure. It's like a queue, but you can get added to or taken out of either end. So you can add to the front, take from the front. You can add to the back, take from the back. That's your deck here. So to get at something in the middle, right, you have to work your way from the front or work your way from the back to get to that middle location here. Totally up to you. Similar to a stack, we'll build our own stacks later. It's a lot of fun, I promise. You'll have some fun with it. So again, depending on what you want to do here, maybe this is the right model for you. Front, back, size, those sorts of things. Find is really handy. So all of these ways of storing data that we've looked at from the standard template library, we can use some fun algorithms on. Let's include algorithms, like the funniest thing to include. Okay, I don't know. You can ask it to find a particular value, starting at some iterator, ending at some iterator. So if you wanted to give it the beginning and give it the end, sure, perfectly fine. If you want to limit it to say, hey, only look from here to here, It's up to you, perfectly fine. You just, whatever iterators you give it will go from front to back here and go look for that value. So find returns the iterator. If it doesn't find it, it gives us the last, right, which is the end. There is actually no value there at the end, right? We don't want the last. So we can go through and find it ourselves. This ways that it goes and finds it. As long as it's not the end, right? We did find it. It is the end. We didn't find it. So we could write our own find essentially if we wanted to. But this idea of the standard template library, there's all sorts of stuff built in. We don't need to reinvent the wheel, although we will go reinvent the wheel later building our own data structures. But that's an exercise with a reason, I suppose, to help you better understand the performance implications of our various data structures. They're pretty fun. And you folks are doing great, I think. Oh, and sort. That's right. There was one last one. So you can sort our structures here from a given iterator. I don't know why you'd only want to sort half, but you could, sure. That's fine. But if you want to sort from beginning to end, right, it'll sort the whole data structure for you, which is really nice. So you can add a bunch of numbers and sort them, which is pretty cool. You can also give it these custom compare functions. So if you don't like the descending order, like the default less than, you can tell it a different way to sort. This is where it starts to get crazy. If you want to sort in a different manner, here, we can. So this one here, we're writing our own function with a true or false for how do we want to sort these things, right? Given two values, how are we sorting? So we can give it a different sorting function here if we want, which is kind of fun. What is a C++ string len? Okay, is that really what we want? Just length. Length is easier. Okay, so if we had that, we have a vector of names, don't we? Yeah, we had names. Let me add some more names here real quick. Names.pushback. Let's add that's one of my kids, I guess. Jeb. Pushback. All right, I just wanted a couple here. And Genevieve. So if we wanted to write our own function here, then we write a little Boolean function for this is sort by length, given a string for first and a string for second. I hate I and j. I don't know. I guess first and second is not all that meaningful either, but that's okay. So we're going to return first.length. Is that a function? I think it's a function. Is less than second.length. Right? It'll be a true or false. So we just want to sort by the length of the string here. So if we include algorithm, nope, that was the wrong one. Algorithm, that one. Algorithms. Now we can ask it to sort names. So we can sort my names collection here. Oh, we got to tell it from where to where, right? So names dot beginning, names dot end, and we can sort. So the default sort should be an alphabetic sort, right? When we compare strings, we look at the numeric value, the Unicode value of every character, and we go through and we'll print them out here. So these are in alphabetical order already. Let's mix it up a little bit here, right? So we should get Eric first because E is a lesser letter, the numeric value, and then JA, JE, B, and JEN, right? When they get sorted. Okay, so we sorted that way. If we wanted to do our custom sort, then let's go through and say we want to sort names from the beginning, names to the end, and we want to sort it with my sort by length function. We can sort it. Now this is crazy. You're passing a function by name here, but you can do that because it's fun. Right, we wrote our own sorting function. See if we can sort it by length here. Now we get Jeb first, then Eric, then Jasmine, then Genevieve. It's sorted by length of our names here. because we wrote our own sort function. That's kind of fun. So depending on what you're trying to do here, if you don't like less than, change it. Totally up to you. Right? This also lets you sort things that can't usually be sorted. Right? If we have a collection of something that's not a string or an integer, like numeric value, how do you sort it? I don't know. Like if we had a collection of fighting pets, how would we sort fighting pets? Well, we could write our own function that says, "Hey, sort them by their numeric value." Right? Just get out their number compared to the other one's number. Right? So if you can sort by a way that you want to, it's pretty powerful, which is a lot of fun. Cool. So you folks did great. That was the chapter actually, which is good. So we are getting a little ahead of where we needed to be. That is awesome. Because recursion is going to take a little bit of time, so we can start that next week. So, and I did post the quiz late for inheritance. I apologize. I forgot to post it Wednesday. I posted it Friday. So I made it due next Friday, this coming Friday, so you had a whole week. If that's bad for you, take another day or 2 or 3. It's really okay. Apologize. I try not to post things on Fridays, but I just realized I had forgotten to do it. And some of the other quizzes generally went pretty well. Do you want to go over any of the other questions or answers? Or if you have questions or answers, you can ask me individually. I'm open to whatever works best for you folks. I don't want it to be like a waste of your time if you don't want to listen to quizzes. No one seems excited. So I'll assume if you have questions, you'll come ask me then. Is that fair? Okay, I like that. We're doing great. So we can start on recursion on Wednesday, and then we can pick it up the following Monday, give us time to solve project 1 on the following Wednesday, and talk about the next project. I think that'll go well for us, okay? All right, folks, take care, and I will see you Wednesday. Thanks for hanging out online, everybody. The best way to learn C++ for beginners, ShotStag, there's tons of things you can find online, YouTube tutorials. I've got my own YouTube stuff, but some other people probably produce their videos a little better, I'll be honest. But exclamation point YouTube, if you want my YouTube link, it's out there. Or just search C++ for beginners. They got a lot of good content out there. Yeah, no problem. You take care.